Welcome students. Welcome to our another online session for the course Digital Logic Design. My name is Ali Rahman and this session is specifically designed for the students of Software Engineering 3C. Well students, in this session we will be discussing the solution for your first evaluation, that was the Sessional 1 examination that has a weightage of 10% marks of your total grade. And I hope so you all had performed well in the examination and you don't face any sort of difficulty while extracting the content and solving the paper and utilizing your content and concepts which you've studied in the course. So to start with our discussion, let us skip the introductory slides. Basically, uh, chapter number 1 and chapter number 2 were the prime concern for the paper, and one of the question involves the universal gates implementation, and one involves the tools complement generation from the ASCII code. So let us go through all the questions step by step and see what was the procedure that was required to be solved for the paper, and so that you can also rectify that what are the mistakes which you've done in order to solve the paper. So the question number 1 was, you have to consider your forename in capital letters. So whatever your forename is, you have to consider it in a capital letter, and you assume it as a string. Basically, it's not the combination of characters is basically a string. So whatsoever your forename is, it's basically a string consisting of ASCII characters, and what you have to do is you have to compute the two's complement of that string, and you have to convert your result in the hexadecimal notation. So two simple steps. Basically what you have to do is, the first step is, whatsoever your forename is, you have to first convert it into the string containing ASCII characters. So in the chapter number 1, table 1.7, basically you have to use that table and you have to generate the 7-bit ASCII code for each character that is appearing in the string. So what you have to do is you have to generate the ASCII code. So first step was to generate the ASCII code in binary. So you have to generate ASCII code. Then the second step was you to invert or flip the bits to generate one's complement. And then you to add 1 in your resultant string to generate the two's complement. And the third step was you to convert that binary string, two's complement string, into hexadecimal. So let us go through an example so that you can verify that how you're gonna perform that task. So let us assume that a forename of the student is Ali, for example, A, L, and I. So the ASCII code or the ASCII value for A from the ASCII table is 100 0001. For the alphabet L, we have the ASCII value that is equivalent to 100, 100, 1100. And for I, we have the ASCII value that is equal to 100, 1001. Now this is the converted string in binary, and this is the string that is been considered together rather than considered individually for generation of ones complement and twos complement. So for ones complement, what you have to do is you have to flip the bits, and then for the twos complement you have to add 1 in that. So to start with, we will start flipping the bits here. So let me use some. So it's 0, 1, 1, 1, 1, 1, 0, then again 0, 1, 1, 0, 0, 1, 1, and then again 0, 1, 1, 0, 1, 1, 0. So that is the ones complement that has been generated by flipping the bits. So for the twos complement, what we have to do is we have to add 1 in the whole string rather than adding individually 1 to every character. So we have to add simply 1 at this placement, at the least significant placement. So 1 plus 0 equals 1 with no carry, and that's how the string will repeat itself. 1, 1, 0, 1, 1, 0, 1, 1, 0, 0, again 1, 1, again 0, 0, then 1, 1, 1, 1, 1, and 0. Now the twos complement of that ASCII string is generated. For the final step, what we have to do is we have to make pairs of 4 bits and then simply convert that into hexadecimal notation. So the next step is we have to generate the pairs basically of 4 bits, because each hexadecimal digit consists of 4 binary bits. So this is the first pair. Then this is the second pair. This is the third pair. This is the fourth pair. This is the fifth pair. Let me erase. This is the fifth pair, and for the last 0 we will add 3 zeros to make the sixth pair. Now if you observe that from the binary pattern of 4 bits, this thing is 7, this thing is 8 plus 2 10, 10 plus 1 11, that is B. This is 9, this is also 9, this is F, and this is 0. So the final answer is 0 F 9 9 B 7. Well, that was all for the question number one. So I hope so you follow the same steps in order to solve your question. Now coming to the next question. That was system implementation basically. So what you have to do is you have to follow the block diagram and you have to extract the information from the question so that you can solve that question easily. So if you observe that the information that is been given in the question, that is basically a system that consists of the three input devices, and in case of any valid authentication from any device, that device provides a logic high at the input of the authentication system. So if any of the authentication is proved valid, then that device returns 1, and otherwise that device returns 0 at the output, and that output is fed back as an input to the authentication system that basically processes the information. So how that system will work in order to grant or deny the access to the lab, basically what you have to do is, first of all, what student has to do is, first of all, that RFID card is scanned by the system. So that is the first information. And if the scanning is done successful, which means that if RFID produces 1 at the output, and the next thing is the password, and if that system also produces 1 at the output, then the access is granted. That is the important information that has been given to you in this statement. Well, in the case if you don't want to go through this authentication, then you have to pass through a fingerprint scanning basically. And basically you can override if the fingerprints match, then you don't need to verify the password, or you don't need to verify the RFID card. So that is the input that is of the prime concern and is of the most significant as far as the access is concerned. So you can extract from the terms from the statements that what are the operations that are needed to be performed. So you don't need to simplify the expression simply. If you say if you consider the both of the cases, then for the first case, if RFID returns 1 and uh, the password is correct, so there is the term and between these two operations. So if RFID and password returns 1, then lab access should be granted. So this is the first condition. So be very careful for the statement. And the second thing is that if the fingerprint scanning is successful, or RFID and password is successful, then the lab access is granted. So you can extract this simply without going through any logical detailed implementation, that there should be the AND operation between the RFID and password, and there should be the OR operation between the result of RFID and password with the fingerprint. Well, to start with the solution, that was the system that was the RFID. Let us name it as the RFID input, RFID, PW for the password verification, and FP for the fingerprint scanning, and lab access is the output basically. When the lab access should be 1. So basically this is a system of 3 literals in which the lab access, let me write it above so that we can also solve it here. The lab access basically, that is a function of fingerprint, password, and RFID. So for the first step, you were required to generate the truth table. So Most of the students have done it correctly, and I'm not going to produce all the truth table here, but I can write the combinations here. So if, let us assume that this is the fingerprint, then we have got the password, then we've got the RFID, and we have the output, that is the lab access. So in this particular case, if we don't have any status of fingerprint here, and we are going through the RFID and password verification. So a fingerprint is X, basically X can be 0, X can be 1. So if in that particular case, if password is 1 and RFID is 1, that then in that particular case lab access should be 1. Now coming to the second case, if we've got 1 at the fingerprint, so whatsoever the status of password, whatsoever the status of RFID, the output should be 1. This X represents basically the don't care state, that it can either be 0, it can either be treated as 1. So all those combinations can be represented by X here, and all the other combinations where FP can be 0, or you can say that in a simpler word, I can write it here uh, as 0. Okay, so all those combinations in which the fingerprint scanning is avoided, and you are going through the RFID and password, and if both are producing 1 here, the lab access should be 1, and if you are going through the fingerprint scanning but you are neglecting password and RFID, then in that particular case the output should be 1. So all those combinations in which the fingerprint is 1, the output should be 1. So that was the truth table basically. So you can extract all the 8 combinations in the truth table, but I'm writing in a short form. Now coming to the logic diagram here, so some of the students have done is to extract the sum of in terms of sum of min terms and implemented the function. They have also done it correctly. But as far as the assessment, we can directly consider from this table that if RFID equals to 1 and password equals to 1. So simply there is an AND operation between these two inputs. So we've got an AND gate here. And the input of that AND gate are RFID and the second input is password, and then we've got the OR operation between these two inputs, and third input is basically that is fingerprint, and the output here is lab access, that is the desired output. So as far as the Boolean function is concerned, basically here we are producing the AND operation and then OR operation. So lab access is equal to fingerprint or RFID and with password. Now coming to the third part, that was the implementation with the NAND gate only. So in that particular case, you've studied that how the AND gate is implemented with NAND gate. So I'm just replicating those here. So for NAND gate, let us assume that this is our first NAND gate. with the input RFID and password. That was RFID and password. So we have to convert it into AND operation, then we have to use a NOT gate here by NAND gate. So here basically this AND gate is replicated here. The next step is to replicate the OR gate, to implement the OR gate by using the NAND gate only, and we've studied that how we'll implement the OR gate. So first of all we have to invert the inputs. So I have to use the inverters here to invert the inputs. The first input is inverted and the second input is inverted, and then we have to use the NAND operation between these two inputs. This is basically the lab access. This thing is connected with this thing, and this input is basically the fingerprint, and here we connect the output of this AND gate to the input of this OR gate, and you can see that this will cancel the effect of this gate, and this is the solution. Well, student, that was all for the today's session. And the next session, we will be discussing the simplification techniques like the K maps in order to simplify our Boolean functions so that we can optimize our resources and we can implement the system with minimal number of resources.